All right, so I believe it is recording now. Okay, Lisa, you're 5 minutes late. All right, so we're going to start the class. So this is our 5th lesson in climate change. And this class is mostly a review of grade 9. So we're going to review biogeochemical cycles. And this is important because we want to track the amount of carbon and nitrogen in the ecosystem. And because both carbon and nitrogen contribute to the greenhouse effect, it is important to know that where these gases should be and what the normal system looks like without any perturbations. So reviewing the carbon cycle, the nitrogen cycle, we're not talking about the phosphorus cycle. That was a topic in grade 9, but in climate change, phosphorus is not relevant, so that's not there. And then we'll talk about anthropogenic effects, how humans can affect both of these cycles. All right, so here goes. So if you are a living organism, then you will need the following nutrients to survive and grow. And where are my nutrients? There they are. You will need water, carbon dioxide, nitrogen, and phosphates. So these elements, hydrogen, oxygen, carbon, nitrogen, phosphorus, and sulfur, not listed here, those are the essential molecules and atoms that you need for life to evolve. And in the ecosystem, these atoms and molecules, they cycle, right? They go from different places into other different places, eventually ending up in your body. And when you die, that will be recycled again to make more organisms. So we are all part of a biogeochemical cycle. Bio being life, geo the earth, and chemical chemistry. So we're going to look at just two cycles, the carbon and the nitrogen. So we're going to talk about the carbon cycle first. So carbon is the atom of life, okay? We are carbon-based life forms. Every single living thing on Earth has carbon, okay? That's how we define something to be organic, having carbon. Now, carbon is important for life because carbon is the most versatile element on the periodic table. It is able to make 4 bonds, and because you can make 4 bonds, you can get a lot of branching, so therefore you can make complicated structures. And life is the most complicated structure in the universe. So it is no surprise that we need carbon for our survival. So we talked about last time carbon stores and carbon sinks. So firstly, something about carbon stores. Now, there's a difference between a short-term store and a long-term store. The difference is like pretty intuitive in the name. Short-term store means you only store carbon for a short amount of time. So, for example, you have living things, you have atmosphere and oceans. Right, living things are short-lived. Humans live to about 80-ish to 100. Other animals, mostly shorter lifespans. 80 to 100 years is a fraction of the total age of the Earth. That is a blink of an eye. So we are short-lived. The carbon inside of your body is only temporarily in there. When you die, those carbon will be released back into the environment. Actually, not even when you die. Your atoms are being replaced pretty much all the time. So it doesn't take long, a few years for you to be completely made up of new atoms than before. And so does the atmosphere. The atmosphere recycles nutrients. So you're only in the atmosphere for a couple of years. Even up to thousands of years, that is still a short time compared to the age of the Earth. Okay, 1,000 years is nothing. And the same can be said for oceans. If you dissolve in the ocean, you could be taken by some marine organism. You could be evaporated back into the air. So that's only temporary. Now, long-term stores are, as the term suggests, long-term. That's there for millions of years, and millions of years are significant even compared to the age of the Earth. So examples of this would be underground fossil fuels, the oil that we extract from the ground. Those are long-term carbon stores. If we don't extract them, they're going to be in the ground for the foreseeable future. Sedimentary rocks and ocean floors, those are also long-term stores of carbon. If you don't extract them, they're stuck there pretty much forever. Right? They're not supposed to move into another place. So hence, long-term, time will not really change that. Whereas short-term stores, you don't need to do anything, just give it time and it will move. So that's the difference between short-term and long-term. You got to know which one is which. So here's a summary picture of the carbon cycle. You don't need to memorize this diagram, just know the key aspects. Carbon exists in the atmosphere. And how did it get there? Well, respiration, burning, gas exchange with oceans, they all put carbon into the air. All right? Respiration can come from animals or plants. It doesn't necessarily come from animals. Plants also breathe oxygen and exhale carbon dioxide, but they also do photosynthesis. All right? And human activities that contribute to this is basically fossil fuel combustion. We take carbon from the ground in the form of fossil fuels. Those are supposed to be long-term stores. All right, we take those carbon from the long-term stores and we burn them to release them into the air. And they don't go back. Okay, so we're taking carbon that is supposed to be trapped for millions of years and we're just putting it into the air. So we are disrupting the natural carbon cycle.
Mr. Joe?
Yes.
When plants respirate, though, isn't it they take in carbon and then release oxygen?
That is photosynthesis. I'm talking about respiration.
Okay.
Yeah, plants
What's
do
the
both.
difference?
So I'll show you a picture pretty soon to illustrate the difference.
Okay, thank you.
Okay, you're welcome. And then, plants take carbon, like has been suggested, from the air and make its body. And how do we get carbon? We don't get it from the air, we get it from food. So we eat the plants. And then we take the carbon trapped in the plants. Or we can eat animals that ate plants. So eventually we trace our source of carbon from the air through plants. Right? And when we die, they go into the soil, which sets up the environment for future life and more plants to grow in the soil. And the oceans as well, the fish and the marine organisms, they can obtain carbon from dissolved carbon in the sea. And runoffs from rivers can wash carbon into the ocean as well, and they descended to the floor of the ocean, like SpongeBob SquarePants Bikini Bottom style. They are stuck at the bottom of the ocean pretty much forever. Like they're not supposed to come out anytime soon. It takes geologic events for oceans to rise and become a surface. Then it might potentially come back into the ecosystem. So far we're not really touching the bottom of the ocean, but we are extracting fossil fuels. So that is one key thing that we're doing. All right, so let's look at each of these processes in more detail. So this is a slide from last time, carbon source versus carbon sink. Carbon source is anything that releases carbon in the form of CO2. Okay, so you guys are all carbon sources. You guys breathe out CO2. And a carbon sink will be anything that stores carbon and take carbon from the air, like trees, for example, or oceans. They both take carbon dioxide from the air and stores them either in the ocean or in life. All right, so how carbon changes form. The first two that we'll look at will be photosynthesis and cellular respiration. So the difference being photosynthesis reduces the amount of carbon in the air. So plants and some bacteria, some algae, they're able to perform photosynthesis. Plants take carbon dioxide from the air, so reducing CO2 in the air, along with water and sunlight to produce sugar and oxygen. Okay, we've talked about this already. And in the picture, photosynthesis are performed by that tree in the example. Glucose and oxygen are produced, and then they are consumed by animals via respiration. So cellular respiration, that's something performed in all, well, I shouldn't say all, in all aerobic life. Okay, so all animals definitely perform cellular respiration. We need to eat. Primarily, our source of energy is glucose, sugar. And we need to breathe. Okay, so those two things are essential for survival. We take sugar and oxygen, we mix them together, metabolize it, and we produce carbon dioxide, water, and energy. The energy we use for ourselves, the water we keep, some of them is evaporated away. But the carbon dioxide, we don't really need a lot of, so we breathe the majority of that out of the body. Okay, so then plants can take the carbon dioxide and make more oxygen. So this is a cycle between animals and plants. So we eat each other's waste. Now notice that respiration increases the amount of carbon dioxide in the air. I mentioned before, plants are able to do both. Okay, plants also need to breathe oxygen and release carbon dioxide. It is a misconception to say that plants don't need oxygen. It's just that oxygen can interfere with photosynthesis, so plants don't want a lot of oxygen, but they do need some oxygen. Okay, so that's how carbon dioxide is moved into plants and then into animals and back into the air. So photosynthesis and cellular respiration. You need to know the equations for both. They're just reverse of each other.
Wait, so essentially for plants, if you go back to the slide, would it be like they do photosynthesis and then through the products of photosynthesis, they perform cellular respiration? Is that how it would work?
Not really, because they occur in different places. Photosynthesis is performed in the chloroplast, and the oxygen released are typically, excreted from the stomata. Fresh oxygen is used in the mitochondria to breathe. Okay, now photosynthesis will produce a lot of oxygen, and the plant needs to get rid of it. If that stays in the plant, that interferes with photosynthesis. It slows down photosynthesis. So plants, yeah, it'd be nice to just pass on the oxygen to the mitochondria, but that doesn't really happen.
So does it just like releases all, like most?
It releases it, yeah, it should. Well, there's oxygen 21% in the air, so there's no problem getting oxygen. You see what I mean? The overabundance of oxygen, that is the problem.
Ah, I see. Thank you.
You're welcome. All right, so the other ways that carbon can go from one source to another, a decomposition, if things die, plants or animals or anything for that matter, any living thing, if you die, you will decompose, and this is done through the process of rotting. Bacteria and fungi are required for this to happen, which is why if you want to preserve something, you need to make sure that there is no microorganism there. So if you want to preserve a body part, you typically put it in a fluid such as formalin, because that kills bacteria, so no microorganisms, no decay. If you just leave it outside, well, there's microorganisms everywhere outside, it will eventually decay. Okay, so these are decomposers or detrivores. They break things that are dead down into its elements so that the nutrients are recycled in the soil, more trees can then grow. All right, so another one would be obviously eating, ingestion. Animals eat plants, so that's how we get carbon for ourselves. And then death and excretion, we also poop and we die, and that releases things back into the environment. All right, so moving on. Alrighty, and then there is natural combustion. Like combustion can either be from nature or humans. Natural combustion include forest fires. They do happen from time to time, say Brazil and Australia. And volcanoes also release a lot of carbon dioxide through its fuming. But then what we're really worried about is the human sources. Naturally, this happens from time to time. This should happen in nature to keep nature balanced. Sometimes if there is no forest fire, people will deliberately set fire to a certain part of the forest because they need that forest to burn from time to time to recycle the nutrients. But humans have been undergoing combustion with fossil fuels for the past century, I guess. So burning of fossil fuels such as coal, oil, natural gas, those all release carbon dioxide into the air. Now, normally without humans, these things don't happen. But because humans do this on a colossal scale, this drastically increases the amount of carbon dioxide into the air. We extract carbon from long-term stores underground and put them in the air. Okay, and there's no countermeasure that we have to sequester carbon from the air. We are trying to develop technology to basically suck carbon out of the air. Carbon resequestration is what that's called, but that's still under research. We don't actually have functioning technology that can do that today.
If we sucked carbon out of the air, though, where would we store it?
No, we just convert it into something else. Like I don't know. That's under research. Like it would be great that we could do that, but let's hope for the best.
I see. Okay.
All right. So the main activities: burning fossil fuels. Because of our actions, carbon dioxide concentrations have been all-time high in the past 800,000 years. All right. Humans have only come onto the scene for about 10,000 years. So 800,000 years ago, like we did not exist. There were still apes. So because of this, the drastic increase in a short amount of time causes climate to change because carbon dioxide is a greenhouse gas, as mentioned from the previous class. So this is the source of the problem. A secondary source of carbon would be deforestation, as mentioned last time as well. By cutting trees down, we are inhibiting photosynthesis. Okay, less trees means less photosynthesis. Less photosynthesis means less carbon is absorbed from the air, which increases carbon in the air. To make it worse, if you burn those trees, let's say you cut them down for firewood, that also releases the carbon stored in the trees back into the air. Now, normally we don't burn them for firewood. We cut them down for other purposes. So because we reduce photosynthesis, that increases carbon. So both of these activities, especially the one on top, those are the contributors to climate change with carbon. Okay? Any questions regarding carbon? All right, so moving on to the nitrogen cycle. So the nitrogen cycle is a little bit harder to understand compared to the carbon cycle. Now, nitrogen is also essential for living things. We need nitrogen to build DNA and proteins. Those are essential things. So we obtain nitrogen from our diet, just like we attain any other nutrient. Plants too need to obtain nitrogen. But the problem is you can't get it from the air, despite the air having 78% nitrogen. Because nitrogen, the atoms that bond nitrogen gas together, they're extremely stable. Okay, nitrogen makes triple bonds with each other, so you can't break that down easily. So the 78% of nitrogen, that is utterly useless. So plants desperately need nitrogen, but you can't use the air. It's like you're really hungry and you have a ton of money, but you're in the wrong country. Okay, you go to, I don't know, let's say you go to Europe. Let's say you go to the UK. You have Canadian dollars. You're not spending that. It doesn't matter how much money you have. They probably won't take it. Okay, so you need to convert it into a usable form. Switch to, I was gonna say euro, and then I realized UK doesn't really like Europe, so probably switch to pound and sterling. So N2 is useless. We need to convert it into usable forms. What are the usable forms? Well, those are the nitrates, NO3, and the ammonia, NH4. Okay, so we've learned chemistry before this, so you should know what NO3, 1 - that is a nitrate molecule. I hope you have your periodic table. If not, Google Classroom has one. NH4 is ammonium that has a 1+ charge. That is also a polyatomic ion. Nitrogen is usable in these forms. So plants must find a way to convert useless or inert nitrogen gas into one of these two. And that's basically the nitrogen cycle. Okay, now how does this work? Well, behold. Not to worry, not too many questions will be on the test regarding the nitrogen cycle. We just need to kind of brush through this. Basically, you have a lot of nitrogen in the air, okay? The problem is, how do we use that? Well, the process of nitrogen fixation. Okay, you see that arrow all the way to the right, the longest arrow that points to the ground, nitrogen fixation. You can either fix it by lightning. Lightning generates a lot of energy. You can transform N2 into basically NO3. Oh, sorry, NH3. Right, by doing that, that's nitrogen fixation. Now that's slow. Lightning doesn't happen very often. We can't depend on lightning to produce NH3. So bacteria will do this in the soil. So these are nitrogen fixing bacteria. Their job is to take nitrogen gas from the air, change it into ammonia, and then more bacteria will convert it into ammonium. Basically, ammonia dissolved in water is ammonium. That's NH4. And then that can be used by plants. So plants will then suck it up and use it to build their body. Alternatively, nitrification will convert ammonium into nitrates, NO3s and NO2s. That's also useful for the plants. All right, so basically you need bacteria in order to achieve this. If all the bacteria on Earth dies, so too does the vast majority of life on Earth. Okay, we need those bacteria. Now, plants will then be eaten by, say, animals, and then that's how we get nitrogen into our bodies, by eating the plant, and plants get it from the soil gets it from, well, bacteria and the air. And if plants and animals die, they will be decomposed and returned back into the soil, okay? Now, how do you get it back into the air? Because you can't just keep taking it from the air and not bringing it back. Well, other types of bacteria called denitrifying bacteria, they will convert it back into nitrogen and release back into the air. So this is a cycle. So where do humans come in? Well, humans need to farm, all right? And farming, we need nitrogen, okay? We can water the plants all day, and there's rain. Cool. We're not in short supply of water. And there is the sun, and we're not in short supply of light, and carbon dioxide is actually increasing, so we're not worried about that. But we don't have enough nitrogen in the soil. Plants won't grow if you don't have nitrogen, so we add fertilizer. Fertilizer are nitrogen-rich compounds that we add so that plants will grow. And farmers use a lot of fertilizer. And if you overuse that and it rains, it will wash into the local ecosystem, rivers and lakes. That's called a runoff. That increases the amount of nitrogen in the lakes, and we'll talk about what happens. All right, so how nitrogen changes form. So here are specific details on nitrogen fixation. So when you fix nitrogen, it simply means you convert nitrogen into ammonia. N2 becomes NH3. Okay, and then NH3 is changed into NH4, and this is done through bacteria. Okay, does that make sense? The picture basically tells the story here. You just need to know nitrogen fixation, you produce NH3 and NH4 from N2. So once those bacteria make the NH3 and NH4s, nitrification occurs. Those NHs become NOs. So these are nitrifying bacteria. So a different kind of bacteria would then take the ammonium, the NH4s, and make them into NOs. Both NHs and NOs are useful for plants. Okay, so it becomes nitrite, NO2, and then nitrate. Lightning also does this, but lightning is generally rare compared to bacteria, so that's insignificant. All right, and then the rain washes the nitrates into the soil so that the soils will have those nitrates. Okay, so moving on to the next part. So once you have the NHs and the NOs, the ammonium and the nitrates, plant sucks them up, so uptake, and then herbivores, plant eaters, will then eat the plants. Okay, so that we ultimately get nitrogen from the air, but we don't do that directly. We do that in a roundabout way. It's like money laundering. You don't spend the money directly, you gotta put it through different accounts first. All right, so you have to bring the nitrogen back into the air. You can't just take and not give back. So denitrification occurs. So these are a different kind of bacteria. So we talked about 3 different types of bacteria. So these are denitrifying bacteria. They do the opposite. They take nitrates and convert them back into inert nitrogen gas. Right, and this is important. Without this, we will deplete the atmosphere of nitrogen. But the atmospheric nitrogen remains constant, so this is in perfect balance. So any questions regarding these transformations of nitrogen? I know they can be confusing because they all look similar. Took me a while to learn it myself. Any questions? Alrighty. Okay, so on to human sources. So humans, in addition to farming, we burn fossil fuels, but fossil fuel mostly increases carbon, yes, but then it also has impurities. It has nitrogen mixed in it. So by burning coal, we are also emitting nitrogen. All right, we are emitting nitrogen oxides, so NO and NO2s, those are byproducts. And those are all brown, hazy, and toxic gases. So we increased the amount of nitrogen in the atmosphere in the form of NO and NO2s in the past decades and century. So it doubled in 15 years. And the second one, the major one, is over-fertilization. As I mentioned earlier, farmers want their plants to grow. And they need to give plants what they want, otherwise they won't grow. All right, so plants need sunlight, CO2, water, phosphorus, and nitrogen. Sunlight we have, okay, the sun will always be there. Carbon dioxide is everywhere in the air, so farmers don't actually have to do anything to get carbon dioxide. Well, water exists as rain, and even if it doesn't rain, you can water the crops yourself. You can irrigate your crops, so farmers have been doing that, no problem. We're not in short supply of water when it comes to agriculture. Phosphorus and nitrogen are different. Okay, phosphorus exists in the soil. Plants can also uptake that, but you can also supplement phosphorus by using fertilizers. However, nitrogen is in the air. You can't use nitrogen gas. That doesn't work. So instead, farmers need to apply NH4, NO3 in the form of fertilizer. So nitrogen is a limiting resource. It limits the amount of plants that you can have in a farmland. That's the amount of yield you're going to get in any harvest. nitrogen limits that number. So you need to increase the amount of nitrogen to increase your yield. So to grow more, we need to somehow get more of this, and we do. Okay, so humans started to use nitrogen fertilizers. And well, if you overdo this, you have excess fertilizers in the runoff, and this will lead to a phenomenon called eutrophication. So eutrophication means the excess amount of nutrients in aquatic ecosystems, in lakes and rivers, because the rain washes them ultimately into lakes and rivers. You might be asking, well, how's that bad? I have excess nutrients, and nutrients are a good thing. Well, it's bad because algae thrives on these nitrogen. If you increase the amount of nitrogen in the water, algae, that in the picture, that green slimy substance, they will proliferate, and this is called an algal bloom. And this causes many problems for the aquatic life. Right? They compete with organisms in the ocean. They use up a lot of carbon dioxide. All right? And some bacteria will eat the algae. Those bacteria consume oxygen. And if the bacteria proliferates, they consume more oxygen, you suffocate the other organisms like fish. So that's how they indirectly kill fish. How do they directly kill fish? Well, these algae, they will release a neurotoxin that will basically kill aquatic organism. They don't do this for any purpose. That's just a byproduct of its metabolism. All right. Well, that's bad for local ecosystems. So we need to prevent algal blooms. We need to prevent eutrophication. Typically, we don't want your lakes to be green. We want them to be crystal clear. All right. So here's another picture of eutrophication. Basically, farming. You see that tractor applying fertilizer, and then it rains, and then it washes into the soil, eventually the ecosystem, which leads to the greening of lakes. Those are algae growth.
I have a question.
Yes.
Slightly stupid question, still question nonetheless. If you go back, it says that eutrophication creates an algal bloom, which then creates a neurotoxin that kills many fish.
Yes.
Wouldn't that neurotoxin be commonly present in the water, but at lower levels because of the algae that is present at a normal
Yeah, it all depends on the amount.
Yeah. So couldn't the fish slowly build a resistance if the increase in the neurotoxin is steady? And
yeah, that's a good question. If that doesn't normally pose a threat, there is no reason to build a resistance. Evolution is reactive. It doesn't really, plan ahead. You see what I mean?
Mm-hmm.
Like, you can live with a poison, but if it's in low concentration, it doesn't really affect you. Natural selection wouldn't favor a fish that is resistant to that poison, so it doesn't really help.
I see. Thank you.
You're welcome. All right, so in summary, the biogeochemical cycle is an intricate process. It's in perfect equilibrium in nature. And then humans came, and we basically disrupted the whole thing. We started to release massive amounts of carbon and nitrogen into the air, which changes the balance. So right now, there is a surplus in the amount of carbon and nitrogen going into the air instead of being taken from the air. So that increase still continues today. Our human activities have not ceased to do this. So they will continue to rise, and the climate will continue to change, and the temperature will continue to rise. So we're going to need to address this problem. So in summary, this lesson basically only tells you about the carbon and nitrogen cycles, how that is supposed to be intricate balance, where carbon is stored, and for how long are they supposed to be stored, and how humans are changing that. Same thing with nitrogen, how we are affecting the amount of nitrogen in the air and how that can affect lakes and the aquatic organisms in the lakes. And any questions?
I have a question
Yes.
about eutrophication.
Hmm.
So, like, doesn't it all like kind of go in a cycle? Because then all the algae's just eating up all the like they're using all the nutrients and resources.
Right.
So wouldn't they just die and then things would go back to normal? Like they need an equilibrium.
I mean, yeah, but because we are constantly supplying the rivers with these nutrients, they're just going to proliferate and stay there. That's being replenished by more runoff. You see what I mean?
Yeah.
Even if it is not replenished, you have a temporary algae infestation. That's still bad. Like you still have like these problems with the lakes, even if they disappear soon. Well, you still don't want that. Does that make sense?
Yeah.
All right. Any other questions?
Yes, now that it has been determined that we will be staying at home until May 4, will we have this test online?
Okay, so let me exit this. If you don't have any more questions regarding the lesson, I'm going to end the stream and I'll answer your questions.